Let us now discuss the battery charger circuit where MPPT is integrated inbuilt into the charger scenario. So let us consider this PV module or a PV array, and this PV array is connected to a DC-DC converter, and then the output of the DC-DC converter is connected to a battery that needs to be charged. So you will say this is the DC-DC converter. It has a control input D, the duty cycle input. The voltage across the terminals of the DC-DC converter output is connected to the battery, and therefore the output of the DC-DC converter, the voltage is fixed by the battery because the battery is a source. Across the battery you may have a load connected like this. So you have a load connected like this. Now, how do we charge the battery? The terminal voltage is VB and this voltage is defined. Then what would be the current, charge current? So let us say we want to put the peak power from the panel into the battery. Now let us say PM is the peak power. PM by VB will give you the IB, the peak power that is going out of the DC-DC converter. So IB can be controlled by controlling the duty cycle because VB is fixed, and therefore power can be controlled by controlling the duty cycle as VB is fixed. So that is the strategy that we want to adopt. Sense this current I0 which is flowing out of the terminals of the DC-DC converter, and use that as the feedback. You also provide the PV current IPV and also the terminal voltage of the PV VT, which will be used for sensing the power that is being drawn from the PV module. Now what is the control algorithm that you need to put in here? Let us consider this boundary here, the terminals of the DC-DC converter to which the battery is connected. Now normally if you consider these terminals and the battery is connected here, all this portion PV source DC-DC converter can be considered as a controlled source. Now let us say if it is a controlled voltage source, plus and minus like this. If you have a controlled voltage source, you cannot parallel two voltage sources because there is no impedance in between, and there can be huge circulating currents which can blow up something in the controlled voltage source. So whenever you are having a controlled voltage source, you need to have a series impedance which will limit the current. So if you are having a controlled voltage source, have a series impedance. This is one possibility. But you don't want to control the voltage because the battery voltage is fixed. You can directly control the current. In fact, a controlled voltage source with a series impedance, and if the impedance is inductive, non-dissipative, that will form a controlled current source itself. So what can be also done is, across this boundary where you have the battery, you have a controlled source, and that controlled source you make it as a controlled current source. It has the inbuilt impedance, necessary impedance inbuilt within it, so that there will always be a current limit. Current source and the voltage sources can be connected in parallel. So we will follow this model, and that is what we will introduce into this control algorithm, which is a current controller. Plus the current controller reference will be obtained from the constraint that we want to take maximum power out of the PV. So plus MPPT, maximum power point tracking, both will be included into this, and we will see how we will do that. And we can choose a DC-DC, appropriate DC-DC converter. It could be a buck boost or a buck boost converter. The control logic will remain similar. Let me draw and discuss the schematic for a buck converter based current controlled battery charger. Now, what it basically means is that the PV module or the PV array is interfaced with a buck converter which will charge the battery. So let us draw the circuit schematic. So you have the PV module, PV panel connected to a buffer capacitor CT at the terminals, and this is followed by a buck converter. So I have a BJT switch. Now this BJT switch can be replaced with a MOSFET switch or an IGBT switch, power semiconductor switch, followed by a diode, and I have an inductor, and following the inductor I am not going to place a capacitor. Instead of the capacitor I will connect a battery in this fashion. And across the battery you may have the load or not, like this. So because the battery here fixes the potential across the output terminals of the DC-DC converter, the current through R0 is decoupled from the rest of the circuit operation. So the current I0 through R0 is V battery by R0. Now here you have the battery voltage VB, we will call that as VB. The current through the inductor is as shown here. This will be the current through the battery, IB, and this current will be I0, which is flowing through the external load. Now our point of interest is this current. The current that is going to the battery load combined should be such that maximum power is drawn from the PV array or the PV module. So let us draw the control schema. I have a comparator here, plus, minus, so it compares the feedback signal with the reference signal. I will call the feedback signal as IL. So what I am going to feedback is the current. Recall our discussion, voltage VB being constant because of the voltage source connected across the terminal. It is sufficient to feedback just the current and use that one to control the power. And here you will have IL reference. IL reference for this. Now this error goes through a comparator. So I will connect this to the minus terminal, to the plus terminal I connect ground 0. Of course there is power supply for the comparator. The output of the comparator goes to an SR latch. So I am going to connect the output of the comparator to the R reset pin of the SR latch. There is a set pin also, then there is a Q, the output pin of the SR latch. The output of the pin of the SR latch is going to get connected to this gate drive circuit or base drive circuit in this fashion. So output of the SR latch Q gets connected to the base drive circuit, which will drive this on or off. So how does this operate? Before that there is something we need to connect to the set pin also. So let me have a clock block. So the clock output is connected to the set pin of the SR latch. How does this clock look like? So let me have the time. So I will mark the sticks each of the stick space is the switching time period Ts. Okay, so the clock is in this fashion. At the beginning of every switching time period, you will have a very narrow, very small duty cycle pulse coming like that at the same period, the period being defined by this clock. So the moment this small duty cycle pulse comes to the set pin, it comes and sets the output of the latch on the rising edge. So you have the rising edge. So at the rising edge, we see that Q gets set, and at every start of the period Q is set and then switches on the transistor. Now let us look at the various waveform to understand how this operates. So I will draw the various axes, time axis basically, and I will divide this into two portions. This is the first cycle Ts, and this is the later cycle. So at the start of the cycle, you have a small duty cycle pulse, and that is this clock pulse, and it happens at every starting of the period. Now the moment this clock pulse is given, it sets this SR latch. Q is high. Moment Q is high, there is base drive for the BJT or gate drive for the MOSFET, and this is on, and VT gets connected and the inductor is charging up. The inductor current is growing. Now let me set some reference here. Let me for the moment set a reference which is constant. Okay, clock, then I will set a reference which is constant IL reference. So when Q is high, it is providing the base drive or gate drive to this power semiconductor switch, and thereby the inductor current is integrating and having a positive slope, and that positive slope is V in minus VB, V battery divided by L. So it keeps increasing in this fashion. IL ref is higher than IL. This is IL ref which is higher than IL. So when IL ref is higher than IL, the output of this algebraic summer will be positive, but that is connected to the negative of the comparator, and the output will be low. The reset pin will be low. No change on Q. So it keeps increasing till the point when IL reaches and crosses over IL ref. So the output of the algebraic summer becomes negative, and this becomes positive. Reset becomes positive, and therefore Q will reset and go low. The moment Q goes low, there is no drive for this power semiconductor switch. It will switch off, and the inductor will start freewheeling and start falling. Current will start falling. So if you take this portion of the operation, you will see that if you look at the output of the Q of the flip-flop, it would have been high till this point, and then it resets. So during this period, when this is low, inductor is freewheeling. You know the buck converter operation, it is freewheeling. This is connected to 0 because it is freewheeling like this, and what is connected to the inductor is minus V0 by L, or minus V0 in this case is VB minus VB by L. And then again at the new cycle, there is a clock coming in. This will trigger the SR latch. Q goes high. The cycle repeats. So you will have the inductor current rising, and then at the point when IL reaches IL ref, there is a change in the slope, So it keeps happening in this fashion. So observe that whatever current value you are setting, IL ref, the inductor current, the current that is going to the battery load combined, never exceeds the IL ref. So it is always below the IL ref and gets controlled in this fashion. And this is called current control. It is as though every cycle there is a check for the currents, and the moment there is a overcurrent within a cycle, it is switched off. And then again the power semiconductor switch is switched on the next cycle, and then it is on till the point when the current exceeds the reference current, and again it switches off. So on it keeps doing, and cycle by cycle there is current limiting, and therefore this is a very safe and fast method of doing battery charging through current control mechanism. However, there are some issues which we will now discuss. Consider the inductor current. I will draw the time versus inductor current, and I will keep the markings in such a way that the duty cycle is less than 0.5. I want to show few cycles. Now let us say this is one cycle, second cycle, third cycle, fourth cycle. Now these are the duty cycle gaps. So in the first cycle, duty cycle less than 0.5, second cycle same duty cycle less than 0.5, third cycle like that. So let me mark the upper tip and the bottom tip of the inductor ripple. So let me mark it like that, and the inductor current will stay within this ripple. So during the time of this duty cycle dt, inductor current is going to rise like this, and during the time of the 1 minus dt it is going to fall, rise, fall, rise, fall, rise, fall, so on. Now this would be the normal expected steady state value of the inductor current. Now let us see what happens if there is a disturbance. Now I will introduce a disturbance here. I'll just offset it. Disturbance could have occurred due to any number of reasons. And let's say if this disturbance occurs, the inductor current will start on from here. It's an integrator. It will start on from here with the same slope, V in minus VB divided by L. So it will go parallel to this line. So let me draw it parallel to that line, and then after it hits this top limit, it will go parallel to the downslope of minus VB by L, then upslope, downslope, so on. You see that it progresses in this fashion. And what is the takeaway from this is that whatever there is a disturbance, the disturbance finally decays to 0, and then it the disturbance is removed, and the normal inductance steady state value current flows. Now take the example of another case, T versus IL. Now I am going to increase the duty cycle to beyond 0.5. Same time period, duty cycle is higher, same time period, duty cycle is higher, and so on. So now when the duty cycle is greater than 0.5, what happens? Let me again mark the top and bottom of the inductor ripple. I will keep it same. And what is the steady state normal expected value of the inductor current? Let me first draw that. So this will be V in minus VB by L. This will be minus VB by L, negative slope, positive slope, negative slope, positive slope, negative slope, so on. So this is the normal expected steady state value of the inductor current under duty cycle greater than 0.5 also. Now here also, like here, we will introduce a disturbance. A disturbance has occurred due to whatever the reason. So when you introduce a disturbance, now from this point onwards it will start going parallel to this line. It will have the same inductor slope. So let us say it takes this line, it hits the top value here, that is the IL reference value, then goes down, resets again, because this is the time duration when the Q of the flip-flop is low, hits the the end of TS, when the clock again gives a small pulse and sets the flip-flop, again it will rise, then goes down, continues going down, here it will get reset, so on, and you see that the disturbance starts growing. Cycle by cycle it starts growing, it becomes unstable. So it never converges to the expected steady state value of the inductor current. So when the duty cycle is greater than 0.5, the inductor current will start diverging, and it will not be stable when you do current controlled operation in this fashion, where this is the IL reference. The top of the inductor current ripple is the IL reference. How do we solve this problem? Let us seek a solution and try to find out how to do that and implement that. Let me consider the problem case waveform. Here the duty cycle is greater than 0.5, and we see that if we give a disturbance, the disturbance keeps growing and leads to an unstable inductor current waveform. Now this line here, this top line here, where the inductor current is comparing with that line, is the IL reference line. So let me highlight that with a different color, and let me indicate that. So that is IL ref. So whenever the inductor current reaches IL ref and tries to cross that, then the error changes direction, becomes negative, and then resets the flip-flop. But that is not happening in a proper way when the duty cycle is greater than 0.5. Now let us try to change the shape of this IL reference line. Instead of being a straight flat line, let us introduce some slope. So what I will do is try to extend this axis, and then let me draw a line which is having the same slope as the falling slope of the inductor. Now the falling slope of the inductor here is minus V0 by L or minus VB by L for the case of the buck converter. So we will try to use that same slope, continue it upwards. Now this is the slope line that we will use for this time period Ts. We will repeat the same sloped line for every time period. So using that as a marker, let me repeat the same slope line for the next time period, then the next time period too, and so on. Now this sawtooth type of waveform will become the new IL ref. So when you use IL ref of this nature, you see something nice happening. Now let us take the same disturbance and let me allow the inductor current to go parallel to what is supposed to be the steady state value. So it goes parallel. Now hits the boundary here. It hits the IL reference here, and at this point it tries to cross over, and the comparator goes, the error goes negative. The comparator output will see to it that the reset of the SR latch resets, is asserted and resets the Q value. So thereby it will then start having a downslope, and the downslope is going to be along the same parallel, because the falling slope for the inductor current is minus V naught by L or minus VB by L in this case. So you see that in just one switching cycle, the error has been reduced. So the error is from there on continues to follow the steady state value. So you see that any error quickly converges and the error is removed within a switching cycle. This is the beauty of having this type of a sloped sawtooth shaped ILREF. So you should give the slope here for the ILREF same as the falling slope of the inductor current. Then you are safe and the error will be removed within a cycle. So how to give a slope? Now this was the old ILREF. To this old ILREF, you have to compensate and see that you have this kind of a slope. So this is called slope compensation. So current control with slope compensation will give you the best results, where even if there are errors, the errors will be removed within a cycle and the system will be stable. So this can also be proved mathematically, what I have just shown by graphs. You can refer to literature on DC-DC converters or any of the NPTEL courses on DC-DC converters. We shall now see how we can generate an IL reference which is of this form. It should be in this kind of a sawtooth form and the slope being same as the falling slope of the inductor current. And once we generate that, then our current controlled converter is ready for performing battery charging operation with MPPT.